Okay, so this problem reads, land west of the San Andreas Fault in Southern California is moving at an average velocity of 6 centimeters per year, northwest, relative to the land east of the fault. Los Angeles is west of the fault and may thus someday be at the same latitude as San Francisco, which is east of the fault. How far in the future will this occur if the displacement to be made is 590 kilometers northwest, assuming the motion remains constant? Okay, so we are dealing with a kinematics one-dimensional motion problem along that northwest meridian. So first we're going to identify what is our object. What are we actually caring about that's moving? Well, the object is that landmass. All right, so what is our initial and our final? What begins the motion and what ends the motion? Well, initially is when we start saying, okay, right now in time, the mass is moving. So at the start of our watch. All right, and what about our final? Well, our final is when we hit that 590 kilometers. So when we reach 590 kilometers. Okay, so next up we draw a picture. So here's our picture, there's our landmass. It's moving northwest at 6 centimeters per year. All right, so we have to identify the origin. Well, the origin, let's say, is right at where that mass is located when we start carrying. It's going to move along that northwest, I guess that's that way. The northwest trajectory, this would be northeast. I'll put that the other way. Moves along that northeast trajectory at 6 centimeters per year. And we're going to look at that 1D motion along that trajectory. All right, so what are our players? We have x initial, x final, v initial, v final, acceleration, and our time. So our initial position, well, that's when we start carrying, that's at 0. And we'll say 0 kilometers. Our final position, well, when we reach that 590 kilometers, we know we're moving at 6 centimeters per year, and we're not accelerating. It says it moves at a constant rate. So the final, when we reach that 590, we're also going to be at 6 centimeters per year. Our acceleration is 0, and we don't know the time. So what's going to answer the question of how long it's going to take? Well, how long it's going to take, that's our time variable. So we need to look for an equation in our kinematics relationships that utilizes time, and there's 2 of them. One utilizes initial and final position, which I have, and one utilizes initial and final velocity, which I also have. But that one really doesn't mean anything unless I'm accelerating, and I'm not. So we're going to use that first relationship where x final is equal to x initial plus v initial t plus 1/2 at squared. Now, because my acceleration is 0, this term is not going to be relevant. So we're left with a variation of this equation that's a little simpler for our constant velocity. Now, the other thing we have to pay attention to is that our units are the same. Our positions are in kilometers, but our velocity is in centimeters per year. So we need to convert one or the other. Let's convert our velocities of centimeters per year into kilometers per year so that we can use the same unit for position. All right, so if we have 6 centimeters per year and I want kilometers per year, what do I need to do? Well, we know that if centimeters is on the top, we need to put it on the bottom. I want kilometers on the top. All right, there is, in 1 kilometer, we have 100,000 centimeters. 100,000 centimeters in 1 kilometer. So my centimeters are going to cancel out. and I'm going to be left with kilometers per year. So when I divide 6 divided by 100,000, I get 6 times 10 to the negative 5th kilometers per year. So I'm going to use that in my relationship because now my units match. And now I can solve the problem. So we have 590 is equal to 0 plus 6 times 10 to the negative 5th. Sorry, I put this in wrong here. That should have a negative 2 times our time. So I divide 590 divided by 6 times 10 to the negative 5th, and I'm left with time is equal to 9.8 times 10 to the 1, 2, 3, 4, 5, 6th years. So at that rate, it's going to take an awful long time for Los Angeles and San Francisco to be at the same level. All right, so recognizing our object of interest, recognizing the type of problem we have, that one dimension can be along a northwest meridian. In this case, it is. Making sure we're staying consistent with our units, and using our kinematics problem solving to solve the problem. Good job.